Hello Calc Kids, this is Mr. Bean and welcome back to another lesson in calculus, and today we're going to talk about improper integrals. I need to warn you, this will be challenging. And not because it's necessarily a hard thing to understand, it's because there's so many different types of integrals we've been learning so far, and you got to put it all together into this now. So here's, to start off, let's understand what an improper integral is, and it's actually a pretty basic thing. It's when there's something with infinity going on here. So if you notice this, we are going to have either an infinite limit, so either the lower limit or the upper limit is an infinity, or maybe even both of them, or somewhere within the interval from -1 to 1, you have a discontinuity that's an infinite discontinuity, like a vertical asymptote. Okay, so infinite discontinuity inside that interval. That's what we have. When we have one of those situations, we have what's considered an improper integral. Well, those are a little bit more difficult to evaluate because we're going forever here. Like, can you even figure out what the integral area under a curve is if you're going forever? Well, sometimes you can and sometimes you can't. And so we'll talk about the difference between those in here in just a minute. So let's start off with, if we're going from a to infinity. So we have a continuous function f, we're just going to go from a to infinity. How do we do this? How do we evaluate that? If we have an example like this one right here, well, this is what it looks like. We're going to use a limit. And the limit is we're going to replace the infinity here. Instead of saying an upper limit of infinity, we'll put in a t and then just say have a limit as t approaches infinity. You see, we can't really evaluate an integral plugging in an infinity, but we can say we're going to approach infinity. So that's the only difference here. And then this one, if we're going from negative infinity up until some included value, notice that the b is included. Same up here, the a was included, so that lower limit was part of it, part of the function. So here the b is in the domain of the function. And we're going up until b, so hopefully you can kind of figure out what we're doing here. If we're going from negative infinity to b, what would this be? The limit as t approaches negative infinity. And then we're going to go from t, this time is on bottom, from t to b, because the negative infinity is getting replaced with substituting in a t value. Now this only works if the limit exists. So provided that these limits exist, then this statement holds true. If the limit doesn't exist, then we're not going to be able to evaluate the integral. You won't be able to know, it doesn't actually go to one specific number. We'll talk about what that means here on our next slide after this one. So let's practice with what we have learned so far, and that is, if we're finding the area under the curve from 1 to infinity, that means we're doing this. So just what's the concept here? We're going from 1 all the way to infinity. So we're doing the area under the curve, and we just keep going and going and going. But notice the area gets really, really tiny. Right away it gets small. By the time we're 3, it looks like it's already there. It's not. If you plug in a number, I mean, it's not going to be 0, but it's going to be awfully close. So does this approach a specific number, that area? Well, let's find out. We first rewrite this as the limit as t approaches infinity of, and now we do our integral from 1 to t instead of to infinity. And then I'm just going to rewrite this as x to the -4 with respect to x. And that'll help me a little bit when I'm taking the antiderivative. And then what's this going to be here? So we take the antiderivative, I get x to the -3 divided by -3, and I'm evaluating it from 1 to t. So now we plug in the t, so the limit as t approaches infinity, and yes, it gets tedious writing this limit down all the time. So this is now going to become, plug in the t first, and we get -1 over 3t cubed minus, and now we plug the 1 into this. So we still have the negative, so it's going to be a -1 over 1 cubed. All right, now what does this equal? Well, now we are going to have t approach infinity. And this is where we use the limit. So as this t approaches infinity, that whole fraction here gets closer and closer and closer to 0. So this just becomes 0 plus 1 over 3, or in other words, this equals 1/3. So the area, this area here, is going to a very specific number of 1/3. And what we do is we say that it converges to 1/3. That's what this area is going to be as you go more and more and more off to the right, infinity. So that leads us to some new vocabulary, and that is converging and diverging. So some of you may have had this in pre-calculus. It just depends on what course you had, maybe what book you used, whether you studied these two things, convergence and divergence, and it's not those movies which were not very good. So if it converges we're saying that the improper integral is going to a very specific number. So if the limit exists, then the improper integral is converging to a number. Like in our last example, it converged to the number 1/3. If the limit does not exist, so if we are working through this limit and we find that the limit doesn't even exist, then the integral is said to diverge, and we're not growing towards a specific number. The area doesn't converge to a number, it diverges. Okay, so here's an example of something diverging. So let's see how we set this up. Notice here, the idea is we're taking this area. So you'd think as the area, you just kind of keep going. If we stretch this off way off to the right, it would get really, really close to 0, right? You'd think, okay, well, doesn't that converge? But you cannot just use the graph and make a determination on if it converges or diverges. You have to work through the mathematics and trust your answer there with these rules, not just looking at the graph and assuming that it converges. So let's do the limit as t approaches infinity, and this time it's going to be, what do we have here? The integral from 1 to t of 1 over x dx. And then the next step down will be that the limit as t approaches infinity of, now this is going to be the natural log of absolute value of x and evaluating it from 1 to t. So the t gets plugged in first, although I still have to have my limit here. My limit as t approaches infinity. So now I'm going to have the natural log of t, absolute value of t, minus the natural log of 1. As t approaches infinity, this natural log of super large number is still going to approach infinity. This is just going off to infinity. Minus natural log of 1 is 0, so that one's easy. But this is approaching infinity, and that's why it diverges. It does not go to a very specific number. So that is an example of something diverging. When the limit doesn't exist, it just goes off to infinity like that. When we get to Unit 10, our very last unit of the year for BC Calculus, when we get to Unit 10, we're going to talk a lot more about convergence and divergence with series, and in particular this stuff here with these weird things going on here. This is something that I want to make sure you understand, and that is when you have this situation, 1 to infinity with 1 over x to the something power. So we just did 1 over x to the first power. The example before was 1 over x to the fourth power. So when that power p is larger than 1, it converges. So if you ever have 1 over x to the number that is larger than 1, it's converging. If it is less than or equal to 1, then it is diverging. That power right there, 1 over x to p. So that's kind of an important one to remember. That will pop up a couple times here and there, and we'll have a little bit of that in the practice as well. Okay, this slide, lots of different words on this thing, a whole bunch of words. This first paragraph here is just reminding you something that we've already talked about, okay? So it's just reminding you that this has to be a finite interval and that the fundamental theorem of calculus states that f of x has to be continuous. So what we're going to work with is situations where that doesn't happen. So where we already did where a or b could be infinity, right? It's going off to infinity, so it's not a finite interval. So we had to use a limit to help us understand how to work with that. And then we're going to talk about a situation where f of x might not be continuous. So we're going to see if there's a way to still solve it that way. So if f of x is continuous, so right here, we're continuous from negative infinity to infinity, then c can be a number in the interval, any real number that we're allowed to just split it up. So look at this. If I go from negative infinity to infinity of f of x, I could split this up and go negative infinity to c, and then add the integral from c to infinity. Okay, that's just our rules that we worked with the properties of integrals. So the reason we want to do that is so that then we can use this right here. You can go from negative infinity to a number, and then that same number, we'll use the same number and off to infinity. That number that I would choose, I would always use 0 because it makes it really easy. So this equals, we're going to do the integral from negative infinity to 0, and then what are we doing? E to the x with respect to x plus, now we'll go from 0, the same number, so 0 is my chosen c, to infinity of e to the x dx. Now we can't use infinity to do these integrals, so that's where we're going to use a limit. But the limit is different. So we have two different integrals here that we're using a limit for. So for the first one, we're going to say the limit as t approaches negative infinity, and then we'll go from t to 0 of e to the x dx. Sorry, that's getting a little sloppy. That looks like a 4. That is a t right there, not a 4. T. plus, and now this has an infinity within the integral, so we have to change this and make it a limit. So we're going to say the limit as t approaches infinity, and then we'll say from 0 to t of e to the x dx. So now you have two separate problems that you're working through. If either one of these diverges, then the whole thing diverges. Okay, so let me repeat that. If you find that one of these pieces diverges, then everything diverges. So you have to work through both of them to figure out what's going on. So you may have to pause the video. I'm going to have this next line appear. Here it is. So there's my work here. And then if I go to the next line where I start plugging in some things, so again, I'm going to have this line just appear. So again, you might have to pause to write that whole thing down. So this is where it gets pretty tricky, because if you plug in a negative infinity into an exponent, see, let me rewrite this line up here. So if I have this limit now, I take the approach with the limits. E to the 0 is 1, so this first part is 1 minus, and then here I have e to the negative infinity, which is equal to this, e to the infinity there. So this is actually 0 on bottom. So I'm good to go. I can keep going here. But now the next part, I'm going to have e to the infinity, and that's the problem right here, what I'm writing, e to the infinity minus 1. That part diverges. This is approaching infinity. So if either of these parts diverge, then the whole thing diverges. So that's our answer for this one. So it's not, I have several examples of where it's going to be diverging on these notes, but it doesn't always. The important thing was the setting up part and then going from there, and it's using things we've already been learning, taking the integral and then using your understanding of limits and how that works. All right, we're getting close. Two more problems. For this one, we are now going to look at a continuous function from a to b on the interval, but b, notice here, it's not including b, so it's an open interval on the end here. And that b, it's open because it has an infinite discontinuity, or in other words, the graph of it, if you're looking at a graph, it's like you have a vertical asymptote, so it's approaching that vertical asymptote, and maybe it peels up to the right like that. It goes up forever and ever and ever. So it's a vertical asymptote, and so that's why we can't actually get to the b and include it. Okay, so that's the idea of what we're doing. So how do you do the limit when you have something like that? You do this. You're going to go from b is going to be substituted with a t, and we're going to have t approach b. Now, if you're approaching b, you have to think that you're approaching b from the left, right? If you remember the picture I just drew, you're approaching b from the left side, and that's why you have that. So the other one, if we're going from a to b, but a is the one that has the vertical asymptote, the infinite discontinuity, then what is our limit going to be? Think through it. It's going to be the limit as t approaches a, and then it is from the right side. We're approaching a from the right, so we're going to get closer and closer to a, coming from the right side and working our way back. And so then a gets substituted with our value of t, so that t can approach a. Okay, so that's, wow, that was confusing. Hopefully you understood that. All right, let's try this out. So the way you know is, and I haven't really talked about this yet, but you're supposed to always check for discontinuities. It's a pretty important thing to do. I should have talked about those before. When we look back at these, like our very first examples, there's a discontinuity at x equals 0, but x equals 0 is not in that interval from 1 to infinity, so we didn't have to worry about it. Same here. There is a discontinuity at x equals 0, but it's from 1 to infinity, so we didn't have to worry about that. Well, on this one, we're going to have some discontinuities, because if I factor this, you'd have an x times x plus 4 inside that radical. So you have two discontinuities at x equals 0 and at x equals negative 4. Well, negative 4 is not in the interval 0 to 2, so we can ignore that one. But x equals 0, that's a problem. X equals 0 represents a discontinuity, and it happens at the beginning. So what we're doing is we're in this situation right here. That a is the beginning, and it is a vertical asymptote. I should call it an infinite discontinuity, because it doesn't cancel with the top. All right, so let's set this up then. So this is the problem I'm working with. I'm going to say that this is equivalent to the limit as t approaches, and this is at 0, from the right side. And then I have my integral here. What is it? From t. So instead of a 0, I'm going to replace it with t, and I'm going up to the number 2. Before I start writing this out, I want you to see that, think a step ahead. How in the world are we going to solve this crazy thing? This is u substitution. Yes, it's not going to go away. So u substitution. U is going to equal the thing on the inside here, x squared plus 4x. And then that means that du is equal to 2x plus 4 dx. Divide both sides by the 2x plus 4, and I'm going to have du over, I'm going to factor this because I needed this x plus 2 to cancel. So if I factor this out, it's going to be 2 times x plus 2 equals dx. Okay, now I can start writing this out. So I'm going to have my fraction here. I still have my x plus 2 on top, but now I'll say the square root of u. X squared plus 4x is my u. And then the dx is going to become du over 2 times x plus 2. Perfect. Now that lets the x plus 2 cancel, x plus 2 cancels. And then now I haven't changed these boundaries here, right? Those haven't changed yet, so let's change those on our next step down. So let's write it over here. The limit as t approaches 0 to the positive. And this gets pretty tedious because you're writing this stuff over and over again. T, so the t limit, let's plug that into our equation here for u. So that's going to be t squared plus 4t. And then the upper limit of 2 gets plugged in. 2 squared is 4 plus 4 times 2 is 8. 4 plus 8, that is 12. Okay, big number. So 12. And then what simplifies here? I'm going to have a 1 over 2, and then the square root of u is on bottom, so I'm going to say u to the negative 1 half. du. Holy cow, all that work, we haven't even taken the integral yet. Okay, let's do this. So now I have the limit, and I do apologize. I know there's not a ton of room for you on this. The limit as t approaches 0 from the right. I'm gonna pause my recording so the answer here just appears. All right, so you've got this now. Hopefully that makes sense what I'm doing here. I just wrote the added 1 and divide by that number, but that makes these 1/2s cancel. That's nice. So now I can go to, what does this equal? This is going to equal the limit as t is still approaching 0 from the right side. And I'm now going to have, plug in the 12. So let's do this. Plug in the 12. I have the square root of 12 minus the square root of, what do I have here? T squared plus 4t. And now we have this approach 0. So 0 is getting really, really close to the number 0. That's what t is. So that whole thing is just 0. So it's this whole thing equals the square root of 12. And that's our answer. So this one converges. It converges to that specific number. All right, one more example. This time we're going to have a discontinuity somewhere inside of a and b. So we're going from a to b. And inside the interval, there's some value c where we have an infinite discontinuity, a vertical asymptote going on inside there. So here's a quick little, oh, wait, I should show this. So what do? We take a and b and we split it up. We're going to go from a to c and then from c to b. So we go from a to that vertical asymptote, and then we go to the other side of the vertical asymptote and continue on until we get to b. So here's our example. We have a discontinuity at x equals 0. That's the problem. That's inside this interval. So I have to rewrite this as negative 1 to 0 of 1 over x with respect to x plus, and then we're going to go from negative 1. No, I'm messing this up. Sorry. We ended at 0, so we pick back up at 0, start at 0, and then we go on until we finish the interval up to 1 of 1 over x with respect to x. So we can't actually evaluate it at 0. So this is where we have to do limit. So let's just set up the limits for the practice of it. We're going to say the limit of t is going to replace the 0. But what you have to think about is it the positive side or the negative side? So we're going to go from negative 1 to t of 1 over x with respect to x. So is it approaching 0 from the left or from the right? So if we're going from negative 1 to 0, we're approaching 0 from the left, because we're starting at negative 1 and going towards 0. So that's how we know that one. Plus, and now let's do the limit as t approaches 0. Okay, I'm not going to put plus or minus yet because I want you to think about this. So 0 becomes the t, and then we're going up to 1. So now we're starting at the t and going towards 1. So we're having t approach 0 from the right side. So that's my 0. I'm approaching it from the right. And then 1 over x with respect to x. All right, let's see what happens when we start taking the antiderivative. So I'm going to pause my recording and have the whole next line appear. So now that we have this line, I want you to realize what's going to happen. We're going to plug the t in, subtract the 1, and the problem is that t is approaching 0. So if I'm going to end up with some type of natural log of t, and that t is approaching 0, natural log of 0 doesn't exist. You can't do that. And so it's going to happen here too. I'm going to plug in this t, and I'm going to have the t approach 0. So I can see both of these things, it's going to diverge. So I'm speeding up my answer here, not working the whole thing out, because I could already see it. I could see the t is getting plugged in, t is approaching 0. Boom, that's a big problem right there. So this thing diverges, and I don't have an answer for this one. Okay, that was, I know, pretty complicated. Sorry, the lesson was long. I was trying to get into some good detail for you on this one. So rock that master check, and I'll see you back in our next lesson, which is the last lesson for Unit 6.